This video is dealing with the topic of binary code to gray code conversion. A binary number can be converted into a gray code by two different methods. We look at both the methods in this video. The bits of a binary number, we can represent them as a set B0, B1, B2, B3 as we move from the least significant bit to the most significant bit. And equivalently, the bits of a gray code can be represented with G0, G1, G2 and G3. This is of course for a 4-bit binary number or a 4-bit gray code. Now, how do we generate the gray code values given a particular binary number? The logic will be like this. For any given n-bit number where I is 0, 1, 2, 3, we say that G of I is the XOR of the ith bit and the I plus 1th bit. So, for example, we'll have G of 0, in this case I becomes 0, G of 0 will be B0 plus B1. So, the G0 here and B0 correspond to the least significant bits of the gray code and the binary code. G1 will be B1 XOR with B2. G2 is B2 XOR with the next higher bit, which is B3, and G3 is B3 XOR with B4. This is of course assuming that we are considering a 4-bit binary number, and as the bits would be increasing, the gray code also would expand accordingly. Now let us take the first method of how to convert a given binary number into its equivalent gray code. We are given here the binary number, and that is 0 1 0 1, and that is 0 1 1 0. Now before we start this, let us show our truth table. This is our XOR truth table, and as we can see in the XOR truth table, when both the inputs are identical, A0 B0, the output is 0, or when A1 B1, the output is again 0. It is only when the inputs are different, 0 1 or 1 0, and only in these two cases, do we get an output of 1, right? So we'll apply this logic to this particular example. So let us start. Our first bit is the binary value 0. Now this MSB, we will first copy it down directly, and this becomes also the MSB of the gray code. Now from here onwards, the procedure will be like this. We will take each bit of the binary and XOR it with the next bit. So we'll take 0 XOR 1. When we take 0 XOR 1, this we know is 1. Then we'll take 1 XOR with the next bit, which is 0. So 1 XOR with 0 is, this will give us 1. Then again 0 XOR with 1, this will of course give us 1. 1 XOR with 0 is 1. 0 XOR with 1, since the bits are different, this will give us 1. And now observe here, 1 XOR with 1. This XOR operation, when we carry out 1 XOR 1, here is our row from the XOR table. 1 XOR 1, this gives us 0, and 1 XOR with 0 gives us 1, and therefore our result becomes 0 1 0 1 0 1 1 0. This is of binary. This is equivalent to 0 1 1 1 followed by 1 1 0 1. This is of the gray code. This is how we can convert the binary value into its equivalent gray code. So here we have directly used the truth table to do this conversion. Now we have a shortcut. We can of course refer to this truth table, but if we observe, what this truth table is essentially telling us is that when we take two similar values and XOR them together, the output is 0. For example, 1 XOR 1 is 0. But when we XOR two dissimilar values like 0 1 or 1 0, in that case the output becomes 1. And we can use this shortcut now to bring about this conversion. So let us take again in this example 0 1 1 1 0 0 1 0. This is our binary code, and we'll convert it into the gray code. Now we need not even refer to this table, because essentially what this table says is what we'll be making a shortcut here. If adjoining bits are same, we will write a 0, and if adjoining bits are different, we'll write a 1. So let us start. First, the most significant bit of the binary, it is copied. So this is simply copied, and it becomes the most significant bit of the gray code. But now observe this. Compare two bits which are successive, two adjoining or adjacent uh, bits. So 0 1, two bits. If the adjoining bits are same, write 0, and if they are different, write 1. So these two bits are different, so we write 1. Again 1 1, adjoining bits are same, so write a 0. 1 1, adjoining bits are same, write a 0. 1 0, adjoining bits different, so this we put it out as 1. Same adjoining bits, 0. Different adjoining bits, this gives us 1. And this again is different adjoining bits, this gives us 1. So essentially we have used the same truth table, but instead of referring to this every time, we just use a simple logic. If bits are same, adjoining bits are same, write a 0, and if adjoining bits are different, write a 1. And therefore we have the equivalent gray code represented by these bits. Now let us take the example of converting a decimal number to the gray code. Now to convert a decimal number to the gray code, we must follow two steps. The first step is we first convert the given decimal number to its equivalent binary value. So we know this, that this 23, we can convert it into the binary by repeated division by 2. So this is 2, 11 times is 22, that gives us a remainder of 1. Again 2, 5 times is 10, that gives us a remainder of 1. 2, 2 times is 4 with a remainder of 1. 2, 1 times is 2, and there is no remainder. And now 2, since the quotient here is less than 2, 0 times will be 0, and that gives us a remainder of 1. And now of course we take these remainders in the reverse order, and we have 23 of decimal is 10111 10111. And now to convert this bit pattern into the equivalent gray code, we again first copy down the most significant bit of the binary, and that becomes the most significant bit of the gray code. Then we compare these two adjoining values. If the values are different, we write this as 1. Again we compare these two adjoining values. Since these two adjoining values are different, the result here will be 1. Since these two adjoining values are same, we write a 1, we write a 0 here. Since these two adjoining values are same, we write a 0 here. And therefore 23 of decimal can be written as 11100 in the gray code. This is how we convert a decimal number into a gray code. Of course, by first going through the intermediate state of converting it into a binary number.